Today we are going to talk about modeling with quadratic functions. The first thing you can see here when we're modeling with quadratic functions is what we call the vertical motion model. The vertical motion model is the equation h sub t equals negative 16 t squared plus v naught times t plus h naught. What that means, t, if you can see, t is the time in seconds. H represents the height of an object. The v naught or the v sub 0 represents its initial velocity. And the h naught or h sub 0 here is the initial height. What we're going to do is use this in order to write some equations and figure out some information about some equations. So let's take a look at the first example. A diver jumps off a platform at an initial velocity of 16 feet per second. What quadratic function represents the height of the diver after t seconds of the dive? So what we're going to do is use the equation h sub t equals negative 16 t squared plus v naught times t plus h naught. So what we need to know is the initial height, the initial velocity. So v sub 0 or v naught is 16 feet per second. And we need the initial height, which is h naught or h sub 0. And the initial height, we go over here to the picture, and you can see initial height of 30 feet. So all we do is just plug those numbers in, and we have our equation that represents the quadratic function of a diver who starts at height h and after t seconds. So h sub t equals negative 16 t squared plus 16t plus 30. That is our equation. Now the second part to that is how many feet above the platform will the diver be at its highest point? So when we look at this, the highest point will be that point up there, which is the vertex. In order to find the vertex, we have to do x equals the opposite of b over 2a, and then take that and plug it in. So the opposite of b over 2a, and when we plug it into the function, and this time the function is h of x, or h of t, so h of the opposite of b over 2a. So whatever we get, we plug that in. So what we have to do is go up here and look. What is the b and what is the a value? So our b value is the 16. Our a value is the negative 16. So x, actually it should be t, so this should be a t as well, because we're looking at the variable t in this equation. So t equals the opposite of b is 16, so the opposite is negative 16, over 2 times a, which is also negative 16. So to do the math, we do negative 16 divided by 2 times negative 16, which is negative 32. Simplifies to 1/2. So the x, or the t coordinate, the first coordinate, is going to be 1/2. Now we just have to plug that back into our equation. H sub t equals negative 16 times t squared plus 16 times t plus 30, where we're just putting 1/2 in wherever we saw a t. And we're just going to do the math. What this is saying is after 1/2 of a second, the diver is going to be at its highest point, he or she highest point. So we just do the math here. So negative 16 times 1/2 squared is 1/4. Plus 16 times 1/2 is 8. Plus 30. 1/4 of negative 16 is negative 4. Plus 8 plus 30. So when we do that math, we get h of 1/2 equals 34. So after 1/2 of a second, the height of the diver is going to be 34 feet. So in a half of a second, the diver is at their maximum height, being 34 feet then. And that answers that question. Moving on to the next question. This time, all we want to do is write the actual equation. If Paul hits a baseball straight up in the air, the baseball is hit with an initial velocity of 70 feet per second when it's hit from 3.5 feet off the ground. So once again, we're using that vertical motion model, which is h sub t equals negative 16 t squared plus v sub 0 times t plus h sub 0. What we know is that the initial velocity, which is v sub 0, is 70 feet per second. And we know the initial height is 3.5 feet. So that's h sub 0. And then we just plug it in. So h sub t equals negative 16t squared plus 70t plus 3.5. And that's our answer. Now we want to move on to another type of question, which this type of question, we're actually going to do what's called regression. We've actually done linear regression earlier this year using Desmos. So we're actually going to look at the Desmos calculator when going through this problem. But first, I want to look at question A. So question A says, would this be a linear function, or would a linear function be a good fit for this data? So basically, we're looking at this helicopter here dropping a package, and you can see the drop of the package after 0 seconds is 350 feet, 1 second is 335 feet, 2 seconds is 283 feet, so on and so forth. What we notice is that each time it drops, so like from 0 to 1 second, it's only dropping 15 feet. From 1 second to 2 seconds, when it drops that distance is 52 feet. So from 0 to 1, it's only dropped 15 feet. From 1 to 2, it's dropped 52 feet. And then from 283 to 206, it's actually dropped a distance of 77 feet. And then to go to 96 feet, it's dropped a distance of 110 feet. So what we notice is that each second, the package is dropping quite a bit more than it did the previous time. So when it says, would a linear function be a good fit? We would say no. And the reason a linear function would not be a good fit is because if it's linear, the rate at which it drops should be constant. In other words, it should be the same number. Now, if I were going to do this as an actual data, maybe the first second it drops 15 feet, the second it drops like 17 more feet, the third drops maybe 16 more feet. So if it would stay around that 15 feet, but since it continues to go up, this is not a good fit because what it's dropping is not constant. And even if it wasn't constant, it would still need to be near a constant number, but it's not. So that's not a good fit. So would a quadratic function be a good model for this data? Well, what we can do to see if the quadratic function would be a good fit is take a look at the quadratic regression, which I can do on Desmos. So you'll notice here I've actually already programmed the data in. And you can see how those numbers are already programmed in. So when I go to Desmos, I can look at a regression model just by doing y sub 1 tilde x sub 1, or sorry, a x sub 1 raised to the second power plus bx sub 1 plus c. And this gives me the regression